Hi everyone, it's Lagaya here from Boost Revision. In this A-level chemistry video today, we're going to be talking about redox and oxidation states. Okay, so first of all, let's discuss what redox reactions are. A redox reaction is a reaction in which electrons are transferred. Oxidation and reduction happen at the same time. An example of this would be this reaction between magnesium and hydrochloric acid to make magnesium chloride and hydrogen. There are various ways in which reduction and oxidation can be defined, in terms of the loss or gain of oxygen, the loss or gain of hydrogen, but at A-level or IB, the most important thing is to do with the loss or gain of electrons. So reduction is the gain of electrons, and oxidation is the loss of electrons. You may have already come across an easy way to remember this, which is oil rig. Oxidation is loss, reduction is gain. So remember oil rig to remember which way round oxidation and reduction are. An oxidizing agent is a substance that oxidizes something else. So by oxidizing something else, it itself will gain electrons. A reducing agent will reduce something else, and therefore a reducing agent loses electrons. This means that an oxidizing agent is always reduced, and a reducing agent is always oxidized. At A-level or IB, you'd be expected to be able to identify the substance that is oxidized or reduced, as well as an oxidizing agent or a reducing agent. Okay, so now let's talk about oxidation states. At GCSE, you'd have been expected to identify a redox reaction and identify something that's oxidized and reduced based on the loss or gain of electrons. At A-level, you go a little bit further and you're expected to know about something called oxidation states and be able to identify whether something is oxidized or reduced based on the change of oxidation state. So let's look at the definition of this. The oxidation state of an atom tells you the total number of electrons it has lost or gained. So how do we calculate or assign an oxidation state? Well, there are a few rules for working out the oxidation state of an atom in an element, compound, or ion. First of all, elements always have an oxidation state of 0. This is true whether they are single atoms or molecules. Next, simple monoatomic ions have the same oxidation state as the charge on their ion. So this is true for any ion in group 1, 2 or 3. So sodium, which is in group 1, will have an oxidation state of +1. Magnesium is in group 2, so it will have an oxidation state of +2. And aluminium is in group 3, so it'll always have an oxidation state of +3. For non-metal ions existing as a single ion in a compound with a positive ion, then the oxidation state is the charge on their ion. So for example, in sodium chloride, chlorine is a -1 ion and therefore it has a -1 oxidation state. In magnesium oxide, oxygen is a 2- ion and therefore it has a -2 oxidation state. However, most nonmetals often exist as part of covalently bonded molecules or as part of polyatomic ions, and therefore they can often have different oxidation states. So we'll need the next few rules to work those out. Oxygen will almost always have an oxidation state of -2, unless it's in a peroxide or bonded with fluorine. This is because fluorine is more electronegative than oxygen. So if oxygen and fluorine are in a compound together, then fluorine's oxidation state will be a priority. Fluorine, being in group 7, will always have an oxidation state of -1. Hydrogen will almost always have an oxidation state of +1, unless it's in a metal hydride, such as sodium hydride, because then the metal takes priority. The sodium will be +1, and therefore the hydrogen will be -1, and that's because of this next rule. The sum of all oxidation states in a neutral compound is 0. So for example, in sodium chloride, the sodium has an oxidation state of +1 and the chloride has an oxidation state of -1. +1 and -1 equals 0. Same with the sodium hydride. +1 for sodium, -1 for hydrogen gives a total oxidation state of 0 for a neutral compound. Similarly, for a polyatomic ion, the sum of all of the oxidation states of the atoms in that ion must add up to the total charge on that ion. polyatomic ion you've probably seen before is the sulfate ion, SO4 2-. The overall charge on this ion is 2-, and therefore the sum of the oxidation states of the sulfur and oxygen must add up to 2-. And this allows us to calculate the oxidation states of both the sulfur and the oxygen. We start with the rules, which tell us that oxygen always has an oxidation state of -2. Since there are 4 oxygen atoms in the sulfate ion, we have 4 times -2, which equals -8, and we want the total of the ion to add up to -2. The difference between -8 and -2 is 6, and that means that the sulfur in this ion must have an oxidation state of +6. +6 and -8 equals -2, the overall charge of the ion. Okay, so now that we know how to assign oxidation states, how can we identify them from their names? You may have come across using Roman numerals to indicate oxidation states when learning about transition metals in GCSE or earlier in your A-level course. Because transition metals can have variable oxidation states, we use the Roman numerals after the name of the metal to indicate what oxidation state that metal has at that point in time, i.e. what charge does that metal ion have. Even for non-metals, we can use Roman numerals to indicate positive oxidation numbers. So with this example, we have 2 different versions of the chlorate ion. You may remember from Key Stage 3 or in GCSE that when you name ions that contain both a non-metal and oxygen, we use the ATE ending to indicate that it's not just the non-metal ion by itself, but it's bonded with oxygen. So the chlorate ion tells us that it's got chlorine and oxygen, and in this ion, chlorine has an oxidation state of +1. The oxygen has an oxidation state of -2 as usual, and that gives us an overall charge of -1 for the chlorate 1 ion. But we can have different chlorate ions, and in the second example, chlorine has an oxidation state of +5. Oxygen still has an oxidation state of -2, and there are 3 oxygens, giving a total of -6, so +5 minus 6 still gives us a total charge of -1. There are numerous other examples, but we'll just look at one more for now for illustration. The chromate 6 ion suggests that we have chromium, which is a metal, attached to oxygen in an ion, and that the chromium in it has an oxidation state of +6. We can check this by assigning the -2 oxidation state to oxygen. There are 7 of those, giving us -14. There are 2 of the chromiums, giving us +12, and that gives us a total charge of that ion of -2. In the second example, chromium 3, the fact that there's no ATE on the end reminds us that this is just the metal by itself, and the Roman numerals after it tells us that it's got a 3+ charge and therefore a +3 oxidation state. In this final section of the video, we're going to be looking at redox half equations, which are used to show the loss or gain of electrons in the oxidation and reduction halves of a reaction. So in the example we looked at earlier, we can see that magnesium starts off with an oxidation state of 0, and it turns into a magnesium 2+ ion with an oxidation state of 2+. This means it's lost electrons and was oxidized. We can show this in a half equation by ignoring the hydrogen and chlorine in the reaction. The same thing for the species that was reduced, the hydrogen ion. We start off with 2 hydrogen ions, which gain 2 electrons to make hydrogen the element. So we can see that it's gained 2 electrons and has gone from an oxidation state of +1 to an oxidation state of 0. So you can see here we've got the oxidation half of the reaction and the reduction half of the reaction, showing the loss and gain of electrons, and we completely ignore the chlorine because the chlorine stayed the same on the left and the right. We call this a spectator ion, and we don't need to have this in any ionic equations. Earlier, we were talking about identifying oxidation and reduction by looking at the loss or gain of electrons, but now we've talked about oxidation states, we can also identify the oxidation or reduction halves by looking at the change in oxidation state. If the oxidation state of a species, i.e. an atom, molecule or ion, changes in a reaction, this means it has been oxidized or reduced. So in our example, magnesium changed from 0 to +2, so the oxidation state increased and therefore it was oxidized. The hydrogen went from +1 to 0, therefore the oxidation state decreased and therefore we have a reduction reaction. This is a slightly harder example and one that often trips people up. In this example, we've got the manganate 7 ion, MnO4-, with manganese being a +7 oxidation state. This manganate ion has been turned into the manganese 2+ ion with an oxidation state of +2. Since the oxidation state has changed from +7 to +2, we can tell that the manganese in this reaction has been reduced because the oxidation state has decreased. This means that the manganate ion must have gained 5 electrons to go from +7 to +2. So to build up our half equation, we add 5 electrons on the left-hand side so that now our overall oxidation states balance. We have +7 and 5 electrons on the left-hand side, giving a total charge of +2, and on the right-hand side we have a charge of +2. Now we'll notice that the manganese ions and the electrons or oxidation states balance, but we have these oxygens on the left-hand side and an overall charge of the 1- in the manganate ion and 5 electrons, giving the left-hand side a 6- charge and the right-hand side a 2+ charge. We need to somehow balance the oxygens as well as the charge on the left and right-hand side. To do this, we use hydrogen ions and water. It doesn't matter which way around you do it. Some people like to see that we have 4 oxygens and therefore we'll make 4 water molecules. So we place the 4 water molecules on the right-hand side. Those water molecules mean that we must have 8 hydrogen ions on the left-hand side to balance out the H's, and this now gives us a total charge on the left-hand side of +2 and on the right-hand side as well. Some people prefer to think about it with the charges first, so the -6 charge on the left-hand side needs to become +2, so we add the 8 H+ ions on the left-hand side to bring the charge up to +2, and now the 8 H+ ions can react with the 4 oxygens to make 4 waters on the right-hand side. This now gives us the balanced half equation for the reduction of the manganate 7 ion to the manganese 2+ ion. Note that this is what happens in acidic conditions. Acidic conditions will mean we have excess H+ ions floating around in the solution. But you may also be expected to balance a half equation like this in alkaline conditions. In this case, we need to use hydroxide ions instead of hydrogen ions. So the first 2 steps are the same. We identify the change in oxidation states and add the electrons to the correct side to make the oxidation states balance. But now instead of using H+ ions, we need to use OH- ions to balance out the charges and the oxygens and hydrogens. This is where I find it easier to look at the charge first of all. The left-hand side has a total charge of 6-, and the right-hand side has a total charge of 2+. So how many hydroxide ions do we need to take the charge of the +2 on the right-hand side and make it equal to the -6 on the left-hand side? Well, we need 8 minuses from the OH- ions. So we add 8 OH- ions to the right-hand side, and these 8 hydroxide ions can now balance with 4 water molecules on the left-hand side, giving us the balanced half equation for the reduction of the manganate 7 ions to manganese 2+ ions in alkaline conditions. And finally, you'd be expected to be able to put together 2 half equations to make a full ionic redox equation. In order to combine 2 half equations to form a full ionic equation, we need to first make sure the number of electrons is equal between the oxidation and reduction half of the equations, because if one species lost electrons, the other species must have gained the same number of electrons. In our easy example, the number of electrons is already the same. We've got 2 electrons in the oxidation and the reduction half. So we can simply add the 2 half equations together, which gives us magnesium plus 2H plus 2 electrons on the left-hand side, and magnesium 2 plus H2 plus 2 electrons on the right-hand side. And just like in maths, if we have the same thing on both sides, we can cancel them out. So the 2 electrons on either side cancel each other out, so we can remove this from the full ionic equation, which leaves us with magnesium plus 2H plus going to magnesium 2 plus H2. So looking at our slightly harder example of the reduction of manganate 7 into manganese 2 plus, this might have happened in the reaction of the manganate ion with iron 2 plus. So the oxidation half of the reaction would have been something like Fe2 plus goes to Fe3 plus an electron. But as we said earlier, we need to make sure that the number of electrons in the oxidation and reduction half equations are the same before we try and put them together. So since the reduction equation has 5 electrons on the left-hand side, we need to make sure that the oxidation equation has 5 electrons on the right-hand side. So we multiply the oxidation equation by 5 to balance the electrons, giving us 5 Fe2 plus going to 5 Fe3 plus 5 electrons. We now have the same number of electrons in the reduction equation as the oxidation equation. So we can add the 2 equations together and cancel out the 5 electrons on either side, giving us the full ionic equation, which is MnO4- plus 8H plus 5 Fe2 goes to 5 Mn2 plus 4H2O plus Fe3 plus. And that's it for this video, which covers everything you need to know about redox if you're in year 12 studying A-level or IB chemistry. When you're in year 13, you go on with redox to look at redox titrations and electrode potentials. But for now, just take your time to get your head around this. If you like this video, please make sure you hit the like button and subscribe to this channel for new videos every week on A-level or IB chemistry. Thank you very much for watching and see you next time.